You've got a shopping cart loaded with toys labeled educational and STEM approved. But here's the uncomfortable truth. You probably can't name a single concrete, testable skill any of them will actually teach your kid. That right there is the core problem with buying STEM toys based on the age range printed on the box, instead of the actual capabilities they build. There's a 37% gap between what kids learn in K-12 STEM programs and what entry-level engineering jobs actually require. And that gap gets wider when parents shop by marketing slogans instead of measurable outcomes. I'm Rajiv Patel, and I've spent years testing this stuff, both professionally and with my own kids. You're listening to the STEM Lab podcast. Quick heads up before we dive in, everything you're about to hear, the research, the data, the testing, the script, all of that is 100% human verified and written by real authors like me. The voice you're hearing, though, that's AI generated. Just want to be upfront about that. If you're a regular listener, thanks for being here. I genuinely appreciate it. And if this is your first time tuning in, welcome aboard. We drop new episodes every Monday, Wednesday, and Friday covering STEM toys, learning tools, coding platforms, all that good stuff. Today, we're talking about how to actually choose STEM toys that build real skills instead of just looking good on a shelf. Let's jump in. The truth is, sequential skill architecture matters way more than how old your child is. A 7-year-old who's been building logic skills for 2 years isn't at the same level as a 7-year-old just starting out, even though they're the same age. When you're choosing STEM toys by age, what you're really doing is choosing for skill stage. Age just gives you a rough idea of developmental readiness. The products I'm covering today map to actual capability progressions that I've validated through real-world systems integration work and direct hands-on testing with my own children. Let's talk about what actually matters when you're evaluating these products. First up, concrete capability milestones, not marketing promises. Every single product you look at should tell you what measurable skill your child will be able to demonstrate after putting in 20 to 40 hours with it. When a box says teaches coding, that means absolutely nothing. When it says your child will be able to sequence 8-step conditional loops using physical tokens, now you've got an observable outcome. Here's my test. Could I assess this skill in a 15-minute demonstration? If the learning outcome feels vague or fuzzy, the product doesn't have real instructional architecture behind it. Look for products that actually specify what skills your kid needs before starting and what they'll be ready for next. A quality progression path shows you exactly where this toy fits in a multi-year skill stack. Products designed by actual educators or engineers usually include these progressions. Products designed by marketing teams focus on words like fun and engagement without ever defining what the child actually learns. Next, technical compatibility and infrastructure requirements. Power needs, operating system dependencies, and software ecosystems determine whether a product integrates into a long-term learning setup or becomes this isolated experience that goes nowhere. Check these specs before you buy. What programming environment does it use? Is it some proprietary software that dead ends, or does it bridge to Python, Scratch, Arduino IDE, or other platforms that are actually used in the industry? What about operating system support? Whether it works with Windows, Mac OS, Linux, Chrome OS, iOS, or Android directly affects whether it'll play nice with your existing home setup. Is it offline or cloud dependent? Products that need constant internet connectivity fail during network outages, and they could lose functionality completely if the company shuts down their servers. And what about expandability? Can your child add sensors, actuators, or custom components as their skills advance? Or is it a closed system? I've personally watched 3 different smart robot kits turn into expensive paperweights after the companies shut down their cloud platforms. Buy products with offline functionality and open architecture. Now let's talk about subscription models and consumable costs. The initial purchase price is only part of what you'll actually spend. A lot of STEM products now have embedded subscription requirements for curriculum access, software updates, or cloud features. Others burn through materials like filament for 3D printers, replacement batteries, or project-specific components. Here's what you need to calculate. The 3-year total cost of ownership. That's base hardware cost plus any required subscriptions times 36 months, plus consumables like filament and batteries and expansion packs, plus replacement parts for products with known durability issues. Products that require subscriptions for basic functionality are a poor value unless that subscription delivers continuously updated curriculum tied to actual evolving industry standards. One-time purchase products with durable construction and expandable architectures usually cost you less over time, and they hold their resale value better. Durability for repeated learning cycles is critical. Products designed for classroom use survive getting assembled and disassembled over and over. Consumer products often don't. Check for connector durability. Friction fit versus snap lock versus screw terminal connections all have different failure rates when you use them repeatedly. Look at material quality. ABS plastic components outlast softer thermoplastics. Metal gears outlast nylon. And what about modular repairability? Can you replace individual failed components, or does one broken part brick the entire system? I prioritize products that have published durability testing data or extensive classroom deployment history. Products marketed exclusively to parents often lack the build quality for 200+ assembly cycles. Here's something a lot of people miss: career-relevant tool preparation. The most valuable STEM toys function as stepping stones to professional tools. A product that teaches proprietary block-based coding in some isolated app gives you less long-term value than one that teaches Scratch or Python syntax in environments that working developers actually use. Ask yourself whether each product uses file formats compatible with industry tools, like STL for 3D models or standard protocols for robotics. Does it teach concepts that transfer to professional contexts, things like CAD workflows, version control basics, or circuit design principles? Does it prepare your kid for certification pathways or portfolio building in specific domains? This framework is exactly why I recommend Arduino-compatible robotics kits over proprietary platforms. Arduino skills transfer directly to embedded systems work. Proprietary platforms teach you product-specific workflows with zero professional relevance. Last point here: progressive complexity scaling. Products should offer 18 to 24 months of increasing challenge before your child outgrows them. Single difficulty level toys provide brief engagement, then they collect dust. Quality products include structured curriculum with 40+ hours of guided projects, open-ended building options after you complete the core lessons, expansion packs or community-created content libraries, and a clear pathway to the next level products in the same ecosystem. This is where understanding progressive learning paths becomes critical. Each product should visibly connect to what comes before it and what comes after it in a coherent skill development trajectory. All right, let's get into the specific products. Starting with the Cubeto EPI Learning Robot for ages 3 to 6. Check the link below to see the current price. This delivers screen-free computational thinking through physical programming tokens that children arrange to create movement sequences. This is the entry point. It requires no literacy, teaches sequence and debug thinking, and builds the prerequisite logic skills for all the programming work that comes later. Lab specs. It's battery-powered, takes 4 AA batteries in the robot and 3 AAA in the control board. No connectivity required, works on any flat surface, includes a world map mat, a storybook, and 16 coding blocks. Complete offline operation. No apps, no accounts, no internet dependency. After 30 to 40 hours with this, children can reliably demonstrate 6 to 8 step sequential instructions, debug simple logic errors, and understand basic algorithmic thinking, that input-process-output flow. This forms the cognitive foundation for everything that comes next. On the plus side, zero screen time while teaching genuine programming concepts like sequence, loops, functions, and debugging. The wooden construction is durable, survives 500+ assembly cycles. The tactile block-based programming translates directly to block coding interfaces later. It encourages spatial reasoning and directional vocabulary. No subscription fees or consumable costs beyond standard batteries. Downsides, it's limited to about 18 months before your child outgrows the complexity ceiling. The control board's glossy surface shows fingerprints and minor scratches quickly, and there's no direct bridge product, so you as the parent have to research the next step coding tools independently. Next, Osmo Coding Starter Kit for ages 5 to 8. Check the link below to see the current price. This combines physical manipulation with iPad feedback to teach multi-step programming logic. Children arrange magnetic coding blocks in front of an iPad running the Osmo app, which gives immediate visual feedback as their code executes. This sits in that critical transition zone between purely tactile coding and pure screen-based programming.
Lab specs. You need an iPad from 2017 or newer running iOS 11 or later, the Osmo base, and the magnetic coding blocks for sequence, loop, and parameters. It uses the iPad camera to detect the physical blocks, so no internet required after the initial app download. The base works with Fire tablets if you get a separate mount that's sold separately. Scale outcomes. Children master nested loops, parameter modification, and function calls through 60+ guided challenges. It develops abstraction skills, seeing how physical block arrangements translate to on-screen code execution, prepares them for the transition to Scratch and block-based interfaces. Pros. The physical-to-digital bridge reduces cognitive load during that screen transition. 3 separate coding games provide varied contexts for the same concepts. The iPad stays stable in the base, which prevents frustration from the device moving around during play. It's a one-time purchase with no subscription required. The blocks store in a compact case for easy integration into multi-purpose spaces. Cons. iPad dependency creates a single point of failure. If the tablet breaks or becomes obsolete, the entire kit loses functionality. It's limited to iOS ecosystem. Android support is still incomplete as of 2026. Camera-based detection occasionally misreads blocks in direct sunlight or uneven lighting, and there's no clear expansion path beyond the 3 included games. Moving on to LEGO Education Spike Essential for ages 6 to 9. Check the link below to see the current price. This is the entry point to programmable robotics using the widely deployed LEGO education ecosystem. This is serious infrastructure, both in terms of hardware expandability and curriculum depth, which justifies the higher price point for families committed to multi-year robotics learning paths. Lab specs. 449 LEGO pieces, including Technic elements, an intelligent hub that takes 6 AA batteries or a rechargeable lithium battery pack sold separately, 2 motors, a color sensor, and a light matrix. Scratch-based programming via the Spike app works on Windows 10 and up, Mac OS 10.14 and up, Chrome OS, iOS 10 and up, and Android. Bluetooth connectivity is required during programming, but it runs autonomously after you upload. Skill outcomes. Children complete 50+ lesson units covering basic robotics, sensor input processing, motor control, and event-based programming. Builds directly toward LEGO Mindstorms and first LEGO League competition participation. Develops mechanical design intuition through repeated build, test, refine cycles.
Pros. LEGO compatibility lets you integrate this with existing brick collections. The Scratch-based programming environment is industry standard for elementary education. There's an extensive lesson library with clear learning objectives and assessment rubrics. The hub and sensors stay compatible with Spike Prime for that progression path. Durable construction handles 300+ build cycles without component degradation. Strong classroom adoption means you've got abundant community resources and troubleshooting guides. Cons: higher upfront cost than competing robotics platforms. Budget around $330 to $380 for the complete set. The rechargeable battery pack costs extra, and disposable batteries create ongoing expense. Bluetooth connectivity can be finicky with older devices. Small Technic pins get lost easily, so you need a dedicated storage solution. And LEGO's proprietary sensor and motor ecosystem limits third-party expansion options. Now we're getting into the Arduino Starter Kit Official for ages 9 to 13. Check the link below to see the current price.
This marks the transition from toy-like programming environments to professional development tools. This is text-based C++ programming using the same Arduino IDE that's employed in commercial embedded systems work. I deployed this with my own 10-year-old after she completed block-based robotics. The learning curve is real, but the professional relevance justifies it. Lab specs: Arduino Uno R3 board. 15 projects with all the required components like LEDs, sensors, motors, breadboard, jumper wires, resistors, and a 170-page project book. You need a Windows, Mac OS, or Linux computer with a USB port. Arduino IDE is free and open source, required for programming. No batteries in the base kit. Projects run via USB power or external 9-volt supply. After completing the project sequence, children understand circuit design basics, can write and debug simple C++ programs, comprehend sensor input processing and actuator control, and demonstrate competency with professional development workflows. That's the code, compile, upload, test cycle. These skills transfer directly to Arduino robotics platforms and IoT projects. Pros: industry-standard hardware and software. Skills are directly applicable to professional embedded systems work. The open-source ecosystem ensures long-term support and component availability. Massive community means extensive troubleshooting resources and project libraries. Components remain useful after you complete the book projects, so children can build custom circuits. No subscription fees or proprietary lock-in. Strong foundation for university-level electrical engineering coursework. Cons: text-based programming represents a significant difficulty jump from block-based environments. Expect 8 to 12 hours of frustration during syntax learning. You need a computer with reliable USB ports. Chromebooks have limited Arduino IDE support. No structured curriculum beyond the 15 included projects, so parents have to source next-step learning materials. Breadboard jumper wires develop intermittent connections after 50+ insertions, and you'll need to replace them. The 9-volt battery holder isn't included, so external power projects require an additional purchase. Next up, Creality Ender 3 V3 SE for ages 11 to 16. Check the link below to see the current price. This delivers FDM 3D printing capability at budget-friendly pricing while maintaining the open architecture and upgrade path of professional equipment. This isn't a toy printer with proprietary cartridges, it's a real manufacturing tool that teaches CAD to physical object workflows using Tinkercad and Fusion 360, understand design for manufacturing constraints like overhangs, support structures, and layer adhesion, and develop troubleshooting skills through print failure analysis. These competencies align with mechanical engineering and industrial design career paths. Pros: standard components and open-source firmware enable an unlimited upgrade path. Auto bed leveling eliminates the most frustrating aspect of budget 3D printing, uses commodity filament spools with no proprietary cartridge lock-in, around $20 per kilogram for quality PLA. Large community support means troubleshooting resources for any issue. Genuine manufacturing capability. This prints functional mechanical parts, not just decorative items. The direct drive extruder handles flexible filaments that other systems struggle with. Cons: the open frame design requires a dedicated 3D printing station with ventilation and fire safety equipment. First layer adhesion troubleshooting is a steep learning curve. Expect 5 to 8 failed prints during initial calibration. The brass nozzle wears when printing abrasive filaments, so a steel nozzle upgrade is recommended for long-term use. The bed surface coating degrades after 200 to 300 prints and requires replacement, around $15 to $20. No built-in camera for remote monitoring, so that's a separate purchase if you want it. Noise level is approximately 50 decibels during printing, which makes bedroom placement inadvisable. Last one, Thames and Cosmos solar-powered robotics kit for ages 8 to 12. Check the link below to see the current price. This combines mechanical engineering with renewable energy fundamentals through 15 different solar-powered robot configurations. This addresses the renewable energy learning gap while teaching gear trains, mechanical advantage, and power transmission concepts that underpin mechanical engineering disciplines. Lab specs: 230-plus pieces, including a solar panel that's 0.3 watts at 2.3 volts, motors, gears, transmission elements, and structural components. No batteries required. Operates entirely on solar power or bright indoor light, minimum 500 lux. No programming interface, this is purely mechanical operation. Assembly instructions via printed manual. Requires a flat workspace and basic hand strength for snap-fit assembly. Skill outcomes: children learn mechanical power transmission, gear ratio calculations, and how different gear configurations produce speed versus torque trade-offs. Develops understanding of solar panel output characteristics, things like light intensity, angle, and power conversion through direct experimentation. Builds mechanical intuition through hands-on iteration, adjusting designs to improve performance. Pros: no batteries or electricity costs. Demonstrates renewable energy principles through direct experience. 15 different configurations provide extended engagement across 40-plus hours. Mechanical focus teaches fundamental physics without screen time. Durable construction survives 100-plus assembly and disassembly cycles. Clear progression from simple to complex mechanical systems. Directly supports renewable energy science fair projects. Cons: the solar panel performs poorly in typical indoor lighting, so you need outdoor use or a dedicated bright lamp. No programming interface limits computational skill development. Purely mechanical operation offers no progression path to programmable robotics. Small gears and transmission elements require organized storage to prevent loss. Limited expansion options beyond the 15 included designs. Let me answer some questions that come up a lot.
What age should you start teaching STEM skills to children? Start STEM skill development at age 3 with tactile, screen-free products that teach foundational logic and spatial reasoning without requiring literacy. Products like Cubetto or basic pattern-building toys establish the cognitive infrastructure for later computational thinking. The critical factor isn't chronological age, it's skill prerequisite matching. A 3-year-old ready for sequential logic instruction benefits more from age-appropriate coding toys than from generic play items. Research from MIT's Media Lab demonstrates that early exposure to structured problem-solving frameworks creates measurable advantages in later programming instruction. However, pushing advanced concepts before prerequisite skills exist creates frustration and potential learning aversion. Match products to observable capabilities. Can the child follow 3-step instructions reliably? Do they demonstrate basic cause-effect understanding? Can they persist through simple problem-solving challenges? If yes, they're ready for entry-level STEM toys regardless of specific age. How do you transition from screen-free coding to text-based programming languages? Bridge products that combine physical manipulation with digital feedback create the most effective transition. The progression follows this architecture: pure tactile coding like Cubetto, then physical-digital hybrid like Osmo, then block-based screen programming like Scratch, then simplified text syntax like Python, then professional languages like C++ and Java. Each stage should span 12 to 18 months with 60-plus hours of practice before advancement. The physical-to-Scratch transition specifically requires products that make the abstract concepts of functions, parameters, and conditional logic visible through immediate visual feedback. I deployed Osmo with my oldest specifically because the physical block manipulation reduces cognitive load during the screen transition. She could focus on logic structure without simultaneously learning mouse and keyboard interface.
After mastering Scratch block structures, text-based Python becomes syntax translation rather than learning new concepts. Expect 8 to 12 weeks of frustration during each transition, regardless of age. The key indicator for readiness: can the child debug multi-step programs independently, or do they require adult intervention for every error? Independent debugging signals readiness for the next complexity level.
Do STEM toys need to connect to apps, or can they work offline? Offline functionality delivers superior long-term value and educational resilience compared to app-dependent products. Cloud-based or app-required toys create three specific risks. Company server shutdowns brick the product, internet outages halt learning sessions, and account management adds friction to spontaneous exploration. I prioritize products with complete offline capability or those where apps provide optional enhancement rather than core functionality. The calculus shifts slightly for products bridging to industry-standard platforms. Arduino IDE or Scratch environments justify connectivity requirements because children learn professional tool workflows. However, purely proprietary apps with no skill transfer value represent a poor investment. Check whether the product can operate without internet after initial setup, whether it stores programs locally rather than in cloud accounts, and whether app updates are backward compatible with older devices. Products designed for classroom deployment typically prioritize offline operation because schools can't rely on consistent connectivity. Consumer products often embed unnecessary app dependencies to capture usage data rather than for legitimate pedagogical reasons. How much should you spend on STEM toys at different age levels? Budget allocation should follow skill development milestones rather than arbitrary age brackets. For ages 3 to 6, foundational logic, allocate around $100 to $150 for 2 to 3 durable products that deliver 18+ months each. For ages 6 to 9, computational thinking and basic programming, budget around $200 to $300 annually for block-based coding and entry robotics. For ages 9 to 13, text-based programming and specialized domains, allocate around $400 to $600 for platforms with 3+-year utility, things like Arduino ecosystems, quality 3D printers, or competition robotics. For ages 13 to 16, professional tool preparation, justify around $600 to $1,000 for industry-standard equipment that builds portfolio-worthy projects. These ranges assume durable products with expandability and resale value, not consumable entertainment toys. Calculate 3-year total cost, including subscriptions and consumables, before purchase. A $350 product with no ongoing costs typically outperforms a $150 product requiring $15 per month in subscriptions over the same period. I evaluate return on investment by dividing total lifecycle cost by estimated skill-building hours. Effective products deliver around $1 to $2 per hour of genuine learning engagement. Products exceeding $3 to $4 per learning hour represent poor value unless they provide direct bridge to professional certifications or portfolio development. Which STEM toys prepare children for actual technology careers? Products teaching transferable skills with professional-grade tools deliver the highest career preparation value. Arduino-based platforms teach embedded systems programming used in IoT device development, automotive systems, and industrial automation. Quality 3D printers teach CAD workflows designed for manufacturing principles and rapid prototyping processes used across mechanical engineering and industrial design. Python-compatible AI kits teach machine learning frameworks identical to those used in data science and AI engineering. Competition robotics platforms like FTC and FRC teach engineering documentation, team collaboration, and iterative design processes that directly mirror professional R&D workflows. Avoid products teaching proprietary platforms with zero industry deployment. They consume learning time without building employable skills. The test I apply: does this product teach skills I could list on a resume or demonstrate in a technical interview?
If a 16-year-old can't translate their experience with a product into portfolio projects or internship applications, it's entertainment rather than career preparation. Focus on products compatible with industry-standard programming languages, standard file formats like STL, STEP, and JSON, and common development environments like Arduino IDE, VS Code, and CAD platforms. These tools teach both technical skills and professional workflows, things like version control basics, documentation practices, and troubleshooting methodologies. Should you buy STEM subscription boxes or individual products? Individual product purchases outperform subscription boxes for families following structured, progressive learning paths. Subscription boxes optimize for novelty and variety rather than skill depth. Each month delivers a new project with minimal connection to previous or subsequent boxes. This creates scattered exposure to multiple concepts without mastery of any. Individual products allow 60+ hours of deep practice with single skill sets, building genuine competency rather than surface-level familiarity. The economics reinforce this. Quality individual products cost around $100 to $400 upfront, but deliver 18 to 36 months of expanding challenges. Subscription boxes cost around $25 to $45 monthly, accumulating to $900 to $1,620 over the same period, while providing less cumulative skill development. I've evaluated 5 major STEM subscription services and found that individual products with strong curriculum and expandability consistently outperform monthly boxes in measurable outcomes. The exception, subscription boxes work for families specifically seeking exposure sampling to identify which STEM domains interest their child. Once interest focuses on specific areas like robotics, programming, or renewable energy, cancel subscriptions and invest in depth rather than breadth.
Here's the bottom line. Choosing STEM toys by age requires abandoning marketing-driven age ranges and instead mapping products to observable skill prerequisites and measurable capability outcomes. Start with screen-free logic building at ages 3 to 6, bridge to block-based programming at 6 to 9, transition to text-based coding in specialized domains at 9 to 13, and deploy professional-grade tools at 13 to 16. Prioritize products with offline functionality, open architectures, and clear progression paths to industry-standard platforms. Calculate 3-year total cost, including subscriptions and consumables, before purchase. Test every product against this framework. Can I articulate which specific, verifiable skill this builds, what prerequisite capabilities it requires, and which next step product it prepares for? Products meeting these criteria justify investment as skill-building infrastructure rather than temporary entertainment. The families successfully building home STEM labs treat toy selection as curriculum design. Each product must defend its position in a multi-year capability development roadmap. That wraps up this episode of the STEM Lab podcast. Thanks for listening. We've got new episodes coming out every Monday, Wednesday, and Friday. If you found this helpful, I'd really appreciate it if you could leave a 5-star rating and write a quick review. That's genuinely how other people find the show, and it makes a real difference. And go ahead and subscribe or follow so you get notified the second new episodes drop. Talk soon.